Monday to Friday.
From 9 a.m.
This is Views and News with Clarence Ford.
Only on Cape Talk.
It is 9:38. Welcome back, Views and News through till 12 with me, Clarence, and a very big appointment with the naked scientist. Welcome, Dr. Chris Smith. It's good to have you with us.
Morning, Clarence. How are you?
I'm good. I did lie awake last night. We were speaking yesterday, a fascinating interview with a cosmologist, and he was talking about the center of the universe. And I think what the thought that he left me with was, regardless of where you are, if the universe is that infinite thing, regardless of where you are in the universe, then you are at the center of the universe, aren't you?
Yep, and it's really boggling your mind, isn't it? But if you think about it, if the universe was infinitesimally small and you're at the centre of it, then you make that universe infinitely big. You're still at the centre of it wherever you go because it's infinite in all directions. Therefore, you're always at the centre. That's the argument. And it does make sense, but there's another reason why it confuses people, which is when we look out into the universe, you can see this entity called the cosmic microwave background radiation. And this was, in fact, a number of decades ago now, the thing that gave us, or the insight towards the existence of the Big Bang. It was kind of the smoking gun, because what happened is that the universe expanded very, very quickly from one point in space where it started, and it grew incredibly fast. And we can then look in any direction in space and we can see this radiation coming to us. And when the universe was very small, those radio waves would have been very, very close together, very high intensity radiation. But because the universe has expanded and inflated, it has effectively stretched out or redshifted that radiation. So now we see it in a very different wavelength, much, much longer. And you can use this as evidence that the universe has grown and inflated. But people often say, well, hang on a minute, if we're out here in the Milky Way, and we're a younger sort of galaxy, not that young, but younger than some, why do we still see the same microwave background radiation coming from all directions towards us? Does that mean we're at the centre of the universe? And it's precisely that reason that the universe is infinitely big in all directions, therefore you would see it coming from all directions. But also, there's a very simple explanation, which is when the universe first formed, all the stuff, all the matter, all the entities were very close together, sharing the same energy. If you then make all the space between them bigger, they don't have to move anywhere. They're just spread out because space has got bigger, which means all those bits and entities and materials have been spread out, and they're then sending you the energy they had from all directions. So it looks like you're at the centre of the universe for that reason. Very, very mind-bending stuff, but a bit difficult perhaps for early in the morning, but fascinating nonetheless.
And I don't think it's going to ease my sleeplessness on the topic, but let's go to a voice note.
Good morning, Clarence and Dr. Chris. Dr. Chris, you did an interview with the Professor Wai, the CEO, regarding sweeteners linked to heart diseases. With the doses of sweeteners, has he discovered how long do sweeteners last in the digestive system? Since sweeteners take longer to digest compared to sugar, are there any effects with the longer the sweeteners stay in the digestive system? Is it exaggerating the effect of the heart diseases? Regards, Luke.
Hi, Luke. Yeah, you're referring to a piece we ran on The Naked Scientists a couple of weeks ago. And if you want to listen to that interview, it was with Yihai Chao, who's a researcher at the Karolinska in Sweden. He published the paper in one of the science journals. And their finding, in a nutshell, was inspired by one of the members of the laboratory team drinking diet drinks at lab meetings. And they said, why don't we find out what the sweeteners do to our animals that we study to look at heart disease? So they started feeding their mice, which are predestined to get the mouse equivalent of human heart disease, with small human-relevant doses of the artificial sweetener aspartame. And they followed up what happened to the health of the blood vessels in these mice compared with mice which were otherwise identical but eating normal mouse food. And they found a statistically significant rate of increase in the formation of the damage areas in the blood vessel walls and the extent to which those things grew and narrowed blood vessels. And their theory was that because the sweeteners cause a big release of the hormone insulin into the bloodstream, because the body anticipates that a sweet thing means sugar, and sugar means high blood glucose, and high blood glucose needs insulin to control it. You get a big surge in insulin, which then signals to the blood vessel walls to deal with the insulin surge and the glucose surge, and that has an effect of increasing inflammation in the wall of the blood vessel, which promotes and provokes arterial disease. That was their theory. Now, this is in mice, so we've got to be really cautious about how we extrapolate that to humans, but they said to me that they've stopped drinking diet drinks with aspartame in it because they're worried about it. But these things don't last very long in the body. Aspartame is 2 amino acids, the building blocks of proteins glued together, and when it goes through the digestive tract, it actually breaks apart. Unfortunately, one of the products of it breaking apart is methanol, which is not very good for you either, but it does break apart quite rapidly. But the key thing is the signal is to produce a big surge in insulin. So the stuff doesn't actually have to be even absorbed into the body. It just breaks down in the intestine, but activates all these receptors that tell the body, hey, I'm eating loads of sugar, produce loads of insulin. And that's the danger. So it doesn't have to last very long in the body to provoke that big surge in insulin, and it's the big surge in insulin that appears to increase the likelihood of damage to blood vessels.
Then there's Ray. Ray wants to stay on the cosmos. His question, Naked Scientist, please tell us, can one black hole ever be sucked into another? And what would happen if it did?
The answer is, Ray, yes, absolutely. And scientists have now documented this happening. And one of the reasons why the discovery and the Nobel Prize being conferred for gravitational waves on a number of researchers, including Kip Thorne back in 2016, is because when enormous entities like black holes in space bash into each other, they tear, rip, or vibrate the fabric of space. And that vibration propagates through space-time to us, and we can pick it up. And this has now been documented since. We have gravitational wave detectors on the Earth in a number of places, and they can see, in inverted commas, these distortions in space-time propagating to us from different parts of space, and the pattern of distortions that they see corresponds to what our theories of what would happen if black hole-sized objects were merging. So we do believe that black holes do merge. We think we've got observations based on gravitational waves of this happening. What would happen, or what does happen when it happens? Well, you have one very gravitationally active object engulfing another. Well, they would basically merge and make a black hole with the mass of the two of them joined together. That's the bottom line as to what would happen. And we think, actually, when you look out into the universe, you do see some big and some smaller black holes. And we believe that the reason that some black holes are bigger black holes is because they've eaten a lot more stuff. And some of the things they could have eaten were other black holes, because you're just adding more mass to the black hole, increasing its gravitational intensity of its field, and therefore its influence. And it just becomes a more active black hole as a result of eating another black hole.
I think it's important, since you've raised the issues around artificial sweeteners, that Anne's question just finds prominence. She has a diabetic granddaughter and a husband, and she wants to know what alternatives you would propose.
Well, the thing about this is it depends what sort of diabetes you have. Because if you've got type 1 diabetes, which we used to call juvenile onset diabetes, and this is because it tends to happen when we're youngsters. The peak age of onset is 10 to 12 years old when children get type 1 diabetes. It's caused by the immune system for reasons we don't completely understand, but maybe because it's being tricked by catching a virus of some kind. The immune system destroys all of the insulin-producing cells in the body. So your pancreas becomes unable to produce any insulin, which is why type 1 diabetes is a life-threatening condition, and you require supplementary insulin to make up for what you don't have, and then you can be healthy. Type 2 diabetes, we used to call this maturity onset diabetes because it's more common in older people. This is the one associated with obesity. And this condition is not associated with an absolute reduction in insulin. Type 2 diabetics can actually have higher levels of the hormone insulin than someone who's not diabetic, bizarrely. It's that the body has become blind or deaf to the insulin signal. So one is a condition where there is no insulin. The other is a condition where the body can't interpret the signal from the insulin. So you could argue, well, if the artificial sweeteners are causing a damaging effect, if they are, through provoking a big release of insulin, well, people who can't make any insulin because they're type 1 diabetic are probably not at any increased risk from eating those sweeteners than anybody else. So therefore, they're probably the one group in the population who are going to be okay. The type 2 diabetics already have very high levels of insulin, and they're at risk because they're already obese and they have probably a number of other metabolic problems. And so losing weight is going to be better for them than any risk to their blood vessels caused by a high insulin level because they've already got that. So the people who probably have the most to gain by taking this seriously are people who are not yet diabetic and are worried about their health, and by embracing a healthy diet could reduce their weight and reduce their risk of becoming diabetic. So I think really those are the people, rather than the people at the extremes, that this research might be most attributable to. But again, it is a study in animals. It's very early stage at this stage. It hasn't been repeated, and it needs the next stage of the research, which is what they're doing now, to look in humans to see if there's any evidence that the same thing's happening in us as happens in these experimental mice.
Okay, so autumn nearly upon us in about a week's time, and I guess this question is relevant.
Good morning, Clarence. Could you please ask the naked scientist whether there is scientific evidence of the benefits of vitamin C in fighting colds and flu? Thank you.
This has been looked at, and the evidence is a bit mixed. I think there is one study that showed that in people who take really severe exercise, I think the study was done on Norwegian cross-country skiers, believe it or not, very, very intense metabolic activity. And in those individuals, I think there was some argument that supplementation with vitamin C did help those people reduce their risk of catching coughs and colds and viruses. I don't think there's good sound evidence that just vitamin C in isolation does enhance your immune response. All vitamins at the relevant amounts, in trace amounts in the body, as part of a healthy diet, definitely will help to supplement your immune response and give you the best chance of fighting off infection, because these vitamins, these micronutrients, they're like the oil in your car engine. A little goes a long way. Too much isn't a good thing and can even be bad. So a balanced diet is what we've evolved to eat to obtain these nutrients at the right proportions, in the right way, at the right times, and therefore the best thing to do to stay as healthy as possible and keep your wallet in top quality health, because these vitamins are really expensive, a lot of these supplements, and many people say that it's basically a ruse, and it's a very costly way to make expensive urine when you swallow these vitamin pills, because many of them are water soluble and they just go straight down the toilet because you take too much of the vitamin, like vitamin C, water soluble, you just turn it into urine. Body only needs a certain amount of it. So eat a healthy, balanced diet that's representative of all the right food groups. Make sure you do that, and make sure that you exercise a bit too. That's a much better way to stay healthy and fend off infection than to basically spend a lot of money on expensive supplements, which, if you don't have a defined deficiency in something, they're not going to do you a huge amount of good.
Okay, let's go to the WhatsApp line. Science should yield the same results regardless of who conducts the experiment, but feels like political science often produce wildly different conclusions. Do you think the term science is being stretched too far?
Possibly. What's being referred to here is what we call the reproducibility question. And what we have in science at the moment is a reproducibility crisis, because in recent decades, people have had quite a big shock when they've said, well, when a scientist does an experiment and they tell us how they've done the experiment, I should be able to go get their research, find out how they've done it, repeat the experiments just as they did them, and I should get the same result. Sounds logical, doesn't it? And if we're doing our jobs correctly, that should be absolutely the case. Well, when people have done that, and it's been done quite a lot now, they find that a very significant proportion of the time, in some studies more than half the time, the results are different. Now, why is that? It could be that scientists occasionally are dishonest. I'm sure that happens. We know that some people do lie, so that's a possibility. The other possibility is that the scientists themselves have made mistakes, genuine mistakes, and something was wrong in what they did, but they didn't realise, so they didn't actually do what they thought they'd done, or that the whole thing's built on a house of cards and that there was some other error intrinsic to or a misinterpretation intrinsic to how we made the decisions about what we were seeing and what we were doing and how we were doing the experiments. So this has led to this whole question about making sure we do check and verify and repeat work, and also publish all of the supporting data that go with experiments that we do. So we have in many journals now, they will insist when you send papers to them, some journals say, right, we want all the supplementary data, all the information, all the raw data should be archived with the paper so that people can then pick through it if something comes to light later or they want to independently verify what's been done. Now, with objective science, if I'm running a particle accelerator, I can get all of the data, as much as I can store, that's come off the particle accelerator. I can put that out there and say to people, this is what we found, this is our interpretation. Social science is very different. This is very much an instinctive thing where you're looking at a population and you're asking questions and you're intuiting what you think might be a reason why things are happening. And it's a bit like the difference between a program where there's objective data and a football commentary. When a sports personality or whatever comments on a football game and they come up with all this stuff saying, well, I think this and I think that and they're going to do this, it's all speculation. It's not based on hard data at all. It's their interpretation of the facts as they see them through the lens of their experience. And much of sociology is a bit like that, where you're saying, well, this is what people think, this is what other people thought, this is what we've been thinking for 100 years, this is how we think it fits together in this framework at this point in time. And it's relevant to that population. It's going to be different next week.
Okay, we've got 2 minutes left. Let's see. Keith, Dr. Smith, I heard that there's an insect that lives for 1 day only and then it dies, obviously. What's its purpose with so short a lifespan? Is there any other with such a short lifespan?
Well, there are examples of animals that are, say, in a larval form for many years, turn into a fly and then use their wings to mate and then die. And they only have 1 day to do it in. And if you look at fireflies in New Zealand, I went to the glowworm caves there, for example, at Watomo. Absolutely amazing. Those glowworms are glowing worms for years. They then mature into the fly, and it's born without a mouth. It can't even feed because its purpose is to use its ability to fly off, find a mate, lay eggs, and then go and die. And so really the insect, as you would see it, stage of the life cycle is intended for one purpose only. It's evolved just to reproduce. And the rest of its life, years, is spent as a totally different thing that looks totally different and is there just to grow. So everything happens for a reason, and biology has evolved so that things work the way they do because they have evolved through selection of certain traits and characteristics to be as successful as they can, fitting into their niche in the environment. So if something only lives for a short time, it's because it only needs to.
And that, unfortunately, is all that we have time for. A big thank you to The Naked Scientist every Friday at 9:30. Plenty of questions we won't be able to get to in the time available. Some we'll hold over till next week, but another opportunity to interact with Dr. Chris Smith comes your way next Friday, just after 9. Thank you, 9:30. Thank you, Chris. It is also 3 minutes to 10 o'clock, and Natalie Malchus is standing by with news at the top of the hour.